The purpose of today's activity is to find the speed of sound in air. And you're going to use just a couple of pieces of apparatus to do this. The first thing is going to be a tuning fork. The demonstration that I just used did for you, I used a tuning fork with a frequency of 261 hertz. You don't have to use that particular tuning fork. You're going to be given a set with a whole range of tuning forks. There's 8 or 9 in this set. Pick whichever one you want. Doesn't really matter. Okay? Pick whichever one you want. Hit it against the rubber block. When you do that, it's going to vibrate at the frequency that it has printed on there. That frequency is important. You need to write the value of that frequency down on a piece of paper so that you know which tuning fork you used. Then you're going to hold it over top of this apparatus, which consists of a clear tube and a white tube. The white tube is inside the clear tube, and the white tube has printed on the side of it numbers that correspond to the length of the tube in centimeters. That white tube can be moved up or down to lengthen or shorten the air column. You're also going to have water inside the clear tube and therefore inside the white tube as well. And that water is going to be what allows you, in conjunction with moving the white tube, what allows you to change the length of the tube. You can see here, if I pull this white tube up into the air, the water level doesn't necessarily go down, but the water level is going to, relative to the top of the white tube, is going to go down. The length of the tube is this length right here, from the top of the white tube to the water level. And as I raise that white tube up, okay, then the distance from the top of that white tube to the top of the water is going to be bigger. That's how I'm going to change the length of the tube. All right, I'm going to actually demonstrate this for you now. But I'm going to use a different one that the rubber stopper isn't falling out for. Here we've done the demonstration. You know what you're supposed to hear when I hold that tuning fork over top, right? At a certain length, the sound is going to be amplified. As you raise this white tube upwards, you're going to hear just the tuning fork, but when you raise it to a specific length, that will give you the right length to have the same resonant frequency in the tuning fork as, in the white tube as the tuning fork has, then you should hear it amplified. Okay, you should hear resonance taking place. I want you to record that value. Okay, record the value of the length at which that happened. So for me, I think we found in the demonstration that it was about 31 centimeters. We'd record that as 0.31 meters. Make sense? What did I say the frequency was? 261.6 hertz, I think. You're going to fill in whatever value of the tuning fork that you use there, right? It might be 261, it might be something else. Now, what do I want to do? I'm going to do the same thing, except I'm going to raise it even higher. I'm going to listen for the next time that happens. I'll give you a hint. Okay, if it happened at 31 centimeters, the next one that you hear should be 80, 90, 100, somewhere in that range, okay? So if you hear something at 50 or 60, it's probably not what you're looking for. Okay, you're looking at 80, 90, 100, somewhere in that range. When you get the value of it, record it, write it down. And then move on to a second tuning fork. I got another tuning fork that's now 335 hertz, let's say. Do the exact same thing. The length at which you're going to hear resonance is different. Whatever it is, record it. Okay? And again, listen for the next one. Whatever it is, record it. If you're going to be in the chemistry lab, and the chemistry lab is open, if you're going to work in the chemistry lab, the temperature is 23 degrees Celsius. I measured it just before class. If you're going to work in this classroom, the temperature is 25 degrees Celsius. Wherever you happen to work, make sure you write down the proper temperature because you're going to have to use that temperature for one of the calculations you're going to do. Back for this one. The first analysis question, which appears on the back side of this page, is to find the speed of sound using this equation. 331 plus 0.6 times 25, or 331 times 0 plus 0.6 times 23, wherever you happen to be working. Then, once you've done that, you're going to determine the speed of sound from each of your trials. Now, this is an air column that, as Ethan just said, is a closed air column, so it's going to look something like this. The first harmonic is going to appear here, and we know that that first harmonic ends up being V over 4L. I'm going to actually rearrange this time to solve for V. It becomes 4L times F. whatever length you determined that first resonant frequency to occur at, you're going to multiply that by 4, and you're going to multiply that by the frequency of the tuning fork. That should give you a speed that's hopefully relatively close to the speed that you found in analysis question number 1. Then you're going to do the second trial. In the second trial, we have a standing wave that looks something like this. This is going to say F is equal to 3V over 4L. Notice it's 3 times the first one. It's the third harmonic. There is no second harmonic when we have a closed air column. If we rearrange that to solve for V, we're going to end up getting 4LF over 3. Solve for the speed, and once again, it should be relatively close to the speed that you determined in analysis question number 1. Now, when you go to trial number 3, you're back to the first harmonic again, right? Back to the first harmonic for the second tuning fork. So V will be equal to 4 times L times F. And then for this fourth trial, you're back to the third harmonic for the second tuning fork, 4/3 times L times F. All of these speeds should be relatively close to the value that you had in analysis question number 1. Once you've found all 4 of those speeds, I want you to average them. Average the speeds. So speed 1 plus speed 2 plus speed 3 plus speed 4 divided by 4. And then you're going to do a percent difference. This is the first time that we've done this in Physics 20. You'll do this several times in Physics 30. Some of you may have done it already in chemistry. Percent difference just tells you how far off your value is from where it should be. And the equation for that is your actual value minus your theoretical value over your theoretical value times 100. The actual value that we got is from question number 3. Okay, this value right here. The theoretical value is from question number 1, because that's what it should be, right? 331 plus 0.6 times the temperature. Take whatever you get right here, subtract the number that you got from question number 1, divide it by the number you got in question number 1, take the absolute value sign of that, so make it a positive number no matter what, and then multiply it by 100. If you get a percent difference that is less than 10%, you're in good shape. If you get a percent difference that's more than 10%, it probably means you've made a mistake somewhere in your data collection or your analysis, one of the two.